afternoon, everyone. It's a pleasure for me to introduce our speaker today, who's going to talk to us about mitigating overfitting in machine learning for reservoir characterization with 2D sequence models and joint learning. Our speaker is a PhD student at Georgia Tech who works with Dr. Ghassan Al-Rajid. His research interests lie in solving data-constrained problems in deep learning and signal processing, and he applies this to areas in computational seismic interpretation. Please join me in welcoming Ahmed Mustafa.
Thank you very much for your kind introduction, Yashi, and I think any further introductions on my part will be unnecessary. So I'll just jump right ahead into the presentation. Let me know if you're able to look at my presentation. All right. Yes, so I really just wanted to start off by commenting on the impact deep learning has had on different areas of our lives. It has revolutionized areas from computer vision to natural language processing to autonomous vehicles to medical image interpretation. And some of the key points that have really helped this meteoric rise is the computational resources that are available to us today, the large-scale labeled data sets, allowing us to train powerful machine learning models, and lastly, the development of efficient network architectures and pipelines to process and learn from the labeled data. Now, moving on to the specific topic of seismic interpretation. What I have on the left here is a plot showing the number of search entries containing the term deep learning on the SEG database. SEG, for those who do not know, stands for Society for Exploration Geophysicists. And the data points here show the number of search entries per year for the term deep learning. And you can see there's been an explosive exponential growth for the number of papers on this topic. And that presents us with both opportunities and also challenges. For seismic and geophysics in particular, deep learning has the potential to speed up interpretation workflows and processing times. It can automate repetitive tasks, allowing interpreters and other people involved in the geophysics tasks to focus on other aspects of the area. It can help with critical decision making regarding geophysical prospects. But on the other hand, there's also challenges that have to be navigated before we can realize the full potential of deep learning in seismic. The challenges include proprietary data. Companies are reluctant to share their privately owned data. There's licensing issues. There is a lack of large-scale labeled data sets. And the problem is compounded by the fact that labeling in seismic data sets requires a high level of expert supervision, unlike in, for example, computer vision data sets that can be performed by laymen. So for this talk, I'm basically going to talk about three major points. I'm going to introduce the problem of reservoir characterization, and then I will move on to the topic of designing efficient network architecture. So this talk is about how do we mitigate the problem of overfitting in deep learning for seismic workflows using not only designing efficient network architectures, but also efficient learning paradigms. So these are the three major points that this talk is going to revolve around. So reservoir characterization aims to characterize the reservoir in terms of the various physical properties like acoustic impedance, like density, and it's very important for various geophysical applications like hydrocarbon exploration, to evaluate reservoirs, to estimate their long-term viability for carbon storage purposes, for geological studies of the subsurface, to perform interpretation on the subsurface. One of the means of performing reservoir characterization is seismic inversion, which refers to the process of estimating the reservoir physical parameters, for example, acoustic impedance from seismic data. So what I have, this plot on the left shows a typical seismic trace, a single seismic trace. And then the plot right next to that is an acoustic impedance trace. So this plot here shows a typical migrated seismic section, and a common task for interpretation involves marking out different structures of interest on migrated seismic sections like saltos. Since seismic data is just reflectivity data, as seen from the trace plot on the left, it lacks the low frequency trend. The accuracy of the interpretation can be greatly improved by incorporating knowledge from the physical properties like acoustic impedance. Because acoustic impedance provides the rock properties corresponding to different areas in the subsurface. So this is an additional knowledge that can be used to help with the interpretation task. So just to give a brief overview of how traditional model-based inversion differs from learning-based inversion, model-based inversion begins with a smooth model of the subsurface, M, and then this is forward modeled using a geophysical model to produce the synthetic seismic. The synthetic seismic is compared to the actual observed seismic that is taken at the field. The error computed is used to update the original model. And then several iterations of this process are performed. And in a step-by-step fashion, the estimates about the seismic data and the model are improved. And at the point where the synthetic seismic converges to the observed seismic is the point where the model is assumed to converge to the actual ground truth physical parameters. Learning-based inversion, on the other hand, it works with seismic traces and well logs. Well logs are measures of the physical parameters of the rock properties that you measure at the well locations. And then the seismic traces corresponding to that are used and the seismic traces corresponding to these well logs and the well logs themselves are used to form a training data set. So the xi's here refer to the seismic traces and yi's refer to the well logs. And this training data set is used to train a machine learning model, usually by optimizing some kind of a loss function. The loss function optimizes the learning model's parameters and the training data set using the training data set. And then the optimal model parameters are then used to perform inference on the raw seismic section, all the non-well locations, to produce an estimate of the physical parameters, the complete section. So having done the introduction to how the reservoir characterization looks like, not only the traditional reservoir characterization, but also the machine learning-based reservoir characterization, I move on to describe some of the network architectures that have been used to perform the learning-based inversion task. So the rest of this presentation is going to be about learning-based inversion. So the commonly used architectures we've seen thus far to perform the seismic inversion includes the traditional multi-layer perceptrons. They are one of the oldest architectures that have been used. They involve neurons and dense connections, densely connected neurons, and then these neurons are stacked in layers. The problem with the multi-layer perceptrons is that they assume an unstructured input, so they do not pay any attention to the ordering and structure present within the input, and as such they require a lot of training data, and they are very prone to overfitting. An improvement in this regard is the recurrent neural networks. The recurrent neural networks operate on traces, on sequence data. They assume sequence structure for both input and output, and they explicitly model the input and output data as sequences. And to help with that process, they have a hidden state vector that they compute at every time step, and they pass that vector on to the next time step that helps the network to keep memory of past inputs in order to make predictions of output at the future time steps. So they're especially suited to time series data. They maintain a vector of hidden states to track input history, and they share parameters across time steps, which means that they have much fewer learning parameters compared to a multi-layer perceptron, which greatly reduces the chances of overfitting. Another architecture in this regard is the convolutional neural networks. The convolutional neural networks, they involve trainable kernels that slide over input to make estimations. and by adding successive convolutional layers, you can increase the receptive field, or how much each output activation is able to how much of the input is each output activation able to look at the input. And this is another way that the input can be modeled sequentially to model the output, to produce the output. The problem with all of these architectures is that they all model the seismic data in a trace-by-trace fashion. They only take as input single seismic traces, which means that the inversion that is carried out in a learning-based fashion can only be done in a trace-by-trace fashion, and that can potentially lead to lateral discontinuities in the final inverted property volume. So what I have here is a seismic section, a migrated seismic section, as also shown earlier. And then, as an example, we are interested in inverting the seismic trace just shown here to the corresponding rock property trace. And by doing that in a conventional trace-by-trace manner, we expect to obtain some kind of rock property output, and we expect to have lateral discontinuities in this rock property volume. So what we propose is that by injecting the spatial context of that single seismic trace in the migrated section, we can greatly improve the resolution of the final property volume. So the way we go about doing that is by taking a patch of input seismic, an image of input seismic that is centered at the well log, at the well location, rather than just a single seismic trace. And then we perform 2D convolution over this input seismic patch rather than 1D convolution as before. So, and this 2D convolution is unique in that it's being dilated in the vertical direction, meaning that the kernel increases in dilation over successive layers, which helps to perform sequence modeling on the seismic input in the temporal direction. And then by having a 2D kernel, you're also able to inject the spatial context into the network estimations as it moves over the seismic image patch. So the data set that we used for this study to validate if this hypothesis would work is the very popular SEAM SEAM dataset. It comes with a migrated seismic section as well as a ground truth rock property model. So we uniformly sample a total of 14 wells in this section, and also the corresponding seismic image patches, and not just the seismic traces, not just the single seismic traces, as usually done by conventional sequence modeling based workflows. So we have a seismic image patch centered at the well log, and we have the corresponding well log, and then these form a single training sample for our data set. The seismic patch is a full 751 samples in depth, and it's 7 samples in width. And the well log, the corresponding rock pseudo-log property trace is also 751 samples in depth. And then we have 14 of such well log seismic trace combinations, and they form the training data set for our learning model. The network architecture that we use for this study is shown here. We input the seismic patch to the network, which consists of these 2D convolutional layers, like the one that we just showed earlier. It has a feature extraction module that consists of around 10 convolutional layers. And then the output of the feature extraction module is input simultaneously to a regression module and a reconstruction module. The regression module and the reconstruction module are also based off 2D convolutional layers, but they are much shallower compared to the feature extraction module. The regression module takes the output of the feature extraction segment and outputs the predicted rock property trace at that point. The reconstruction module takes the output of the feature extractor and outputs the reconstructed seismic image patch. And by doing that, it's a multitask learning framework And then by performing these different tasks of rock property prediction and seismic trace reconstruction, we hope to have them share representations with each other, potentially leading to greater generalization performance. So the loss function consists of a term that consists of how well the well logs are reconstructed, which is yi hat minus yi, the mean squared error between the actual ground truth well log and the predicted well log by the network, scaled by a factor alpha, added to the reconstruction loss between the reconstructed seismic image patch by the network and the original seismic image patch, scaled by a factor of beta. So we have the first term called the well log estimation loss and the second term called the seismic image reconstruction loss. And demonstrating the results for the SEAM on the SEAM dataset, I have here the ground truth profile, the ground truth acoustic impedance profile for the SEAM dataset. And then this is a profile that I obtained using a simple one-layer LSTM, which is a specialized class of the recurrent neural network architecture. And you can see that there's a lot of problems with this estimation. It's missing a lot of the details in many places, not only the low frequency trend, but also the high frequency details. Next, I show you the estimated acoustic impedance profile using the one-dimensional temporal convolutional network. It's the temporal convolutional network is a 1D CNN-based architecture that is specialized for sequence modeling tasks on 1D inputs. And it's much better than before. You're able to see the low frequency details. It's able to mark out some of the major transitions happening in the ground truth, but it's still very poor when it comes to the high frequency details. And this can be seen in various places at the salt dome, at the high impedance arch. And coming on to finally the estimation produced by our proposed methodology, you can see that it's much better in many of these places that the other methodologies fail to perform at. So we are able to delineate some of the high frequency details at the top of the salt dome, at the beginning of the high impedance arch, at the transition between the low impedance regions and the high impedance regions. Next, we show you some trace plots taken from this section and overlaid on the ground truth impedance trace for those regions. So we extract impedance traces at the positions specified by the arrows, and we overlay on top the estimations produced by the 1D TCN, the LSTM, and also our own proposed methodology. And it can be seen that the proposed methodology is able to perform much better at predicting the ground truth, which is the red trace in this case, compared to the other methodologies. So looking at the RNN, the LSTM-based method, it's missing not only the low frequency trend, but the high frequency details in many places. The blue trace, which is the 1D TCN-based method, it is much better when it comes to the orange trace. It's much better when it comes to capturing the low frequencies, but it struggles to capture the high frequency details. And the red trace, on the other hand, which is our own method, the proposed method, it's capturing the high frequency details as well as the low frequency trends in the wells very well. And then by having a more thorough regression analysis between the whole of the section, the ground truth section, and the estimated sections produced by the 1D TCN and the LSTM and the 2D proposed methodology, we see that we are able to get the best performance at the Pearson's correlation coefficient and the R-square coefficient compared to the 1D TCN and the LSTM-based methods. So this concludes one part of the study, which was about designing efficient network architectures that are tuned to the specific characteristics of the seismic data for inversion. Next, we move on to designing the learning paradigms, efficient learning paradigms for the inversion task. So overfitting, it's a problem that is plagued by many machine learning problems, especially in the presence of limited data. For the seismic inversion especially, you have a very few wells which serve as the labeled data for the seismic, and then in this case, it's very easy for the algorithm to overfit to the few training data points we have and fail to generalize well to the test data. A potential way to mitigate overfitting is by incorporating knowledge of other surveys of other data sets into the target data set. So what I have here on the left is a different seismic data set and the well log data from a different seismic data set. And then we hope to, by incorporating knowledge of the labeled data from a different seismic data set into the data set that we are interested in, we can improve the generalization performance of the network or the model on the data set that we are interested in, so that it's able to better capture the distribution of the data points not immediately in its training data set. So one very popular framework for that is the pre-training and fine-tuning based transfer learning mechanism that is very popular for image-based tasks. Imagenet is a very popular large-scale data set of labeled objects. And for many computer vision-based tasks, it's a common strategy to pre-train a network on the Imagenet data set for classification. And then by freezing the first layers, the earlier layers of the network, then the resulting network architecture is then fine-tuned on a target data set, the data set which is what people are actually interested in. And the reason they do that is because there isn't many training examples present in the target data set. So it makes sense to pre-train the network on a large-scale labeled data set to capture the similar representations that image data sets share in the earlier layers. And then the final layers that are more data set and task specific, they can then be fine-tuned on the target data set. Now some of the problems that are faced by this pre-training and fine-tuning workflow is firstly the subject matter expertise and the trial and error that is needed to determine the optimal number of fixed pre-training layers. So should we fix 2 layers or 3 layers? This is a matter that is either going to be decided by subject matter experts who have a lot of expertise with the specific area, or you're going to be using you're going to be performing a lot of trial and error to determine the optimal number of pre-training layers that you can later fine-tune on the target data set. Another problem that is faced by the pre-training and fine-tuning based strategy is the large difference between the source and target distribution. So if it so happens that the source and target distributions, they are very different in their nature, then transfer learning from a source data set to a target data set can actually hurt the generalization performance on the target data set instead of improving it, which was the original aim of the transfer learning paradigm. So to overcome this limitation with the pre-training and fine-tuning based strategy, we propose a different learning paradigm, transfer learning paradigm called joint learning. And the idea is illustrated with the help of this simple plot showing a weight space, a parameter space for a neural network that consists of only 2 parameters, in this case theta1 and theta2. And then the different shades of gray show how well that particular region would generalize, the solutions in that particular region would generalize to the testing data set. So we have on the left some seismic data set A. We have a few well logs for that data set, and we have a network that we train on this data set to perform estimations of the well logs for that data set. And by training this network alone, we expect to obtain some solution in the weight space that is optimized for that data set. We could have another data set, we call it data set B. It also consists of a seismic data set. It has well logs embedded within the seismic data set, and we train a different network called network B to perform estimations of the well log on that seismic data set to produce estimated well logs. And by training this network in isolation, we similarly expect to obtain some solution in the weight space that we label B. Now we propose that by having these 2 networks share their knowledge with each other, and I'll go into more detail how they do that. By having these 2 networks share their knowledge with each other as they're training, while they're training on their respective data sets, we can obtain a better, more generalizable region of solutions in the parameter space that would be in proximity to each other. And from we know from the pre-training and fine-tuning based transfer learning strategy that the network weights contain knowledge of the data set that the network was trained on. So one way to have networks share their knowledge of the data sets that they're training on with each other would be their weights. So we impose a similarity constraint between the weights of the two networks. And this constraint, it's not a hard constraint, meaning that the networks are not forced to find an absolutely single solution, but it's a soft constraint. So it's more of a regularization term that encourages the networks to find a region of weights that are in proximity to each other rather than the single solution. So they could find a single solution if that is what optimizes on their respective data sets, but it doesn't have to be the case. And some of the advantages that this learning-based strategy would hold over the conventional pre-training-based transfer learning strategy is that it doesn't require you to set the pre-training hyperparameters as in the pre-training fine-tuning-based transfer learning strategy. So you don't have to decide on the number of pre-training epochs that you should train the network on the source data set. You do not have to decide the number of training samples in the source data set that you pre-train it on. You do not have to decide the number of layers that you should fix before you move on to the fine-tuning stage, and so on. The other advantage with this strategy is the potential for two-way knowledge transfer that can happen over both sides. So with the pre-training and transfer learning-based strategy, the knowledge transfer is only happening one way. So you train a network on the source data set, and then you fine-tune it on the target data set. And by doing that, only the source's knowledge is being transferred to the target, but not the other way around. And not only that, but after fine-tuning the weights on the target data set, it's very likely that the weights become unoptimal for the original source data set. And this is a phenomenon that is very well known in the machine learning literature as catastrophic forgetting, that the network forgets the source task or data set after being fine-tuned on the target data set or task. So this is another potential advantage that this learning methodology holds over the pre-training and transfer learning-based strategy, that it holds the potential for two-way knowledge transfer, that both data sets and both networks will learn from each other rather than a one-way learning scheme. And not only that, it's also dynamic learning, meaning that the networks, they can decide to not learn from the other at all. Meaning that if it so happens that the two data sets are sampled from very different distributions and that transferring the weights or transferring the knowledge of the weights from one network to the other can potentially hurt the generalization performance of the other network, then the networks, they do not actually have to converge to the same solution or within the proximity of the other network. They can always fall back to the original solution, which is training alone on their respective data set. So we validate this hypothesis again with the SEAM data set. So we have the SEAM migrated section as shown before, and the corresponding rock property profile below that. So we have the seismic image patches sampled as before, centered at the well positions, and we have a total of 14 such well logs and corresponding seismic image patches. The other data set that we use for this study is the very popular Marmousi 2 data set. The Marmousi 2 data set also comes with a seismic section, and it also has a ground truth acoustic impedance model. And since this data set it's made by convolutional forward modeling on the original acoustic impedance traces, it's a much easier and cleaner data set compared to the SEAM data set on the left. So we consider Marmousi to be our source data set. So we sample more wells on the Marmousi than we do on the SEAM. So we have a total of 51 wells or labeled training samples on the Marmousi data set. And we have 14 samples or training samples for the SEAM data set. And then thinking in terms of the conventional pre-training and fine-tuning based strategy, you can think of Marmousi being the source data set and SEAM being the target data set. Although, as I just explained earlier, for our own proposed methodology, it would not be quite accurate to think in terms of that, because there would be a two-way knowledge transfer happening rather than a one-way knowledge sharing scheme. So we use the same network as before, which is the 2D spatiotemporal CNN. It takes in a seismic image patch for each data set. It produces, for that seismic image patch, the predicted rock property trace, yi hat, and the reconstructed seismic image trace, which is xi hat. And as before, you have dilations, increasing dilation factor in the kernels as you move to the deeper layers. That would allow the temporal sequence modeling of the seismic simultaneously with the injection of the spatial context allowed by the 2D kernel. So, and we have two such networks because we have two data sets and we have a network for each data set. We have a network training on SEAM and we have another network training on Marmousi. Each network produces estimations for the respective ground truth bell log, and we add them together, the bell log losses for the network on SEAM and the network on Marmousi, to form the regression loss. For each network, we also have the reconstructed seismic traces, so we add in the reconstruction losses for Marmousi and also the reconstruction loss for SEAM to form the total reconstruction loss. And then in addition to this, we have the weight sharing loss that results in the knowledge transfer scheme we just discussed earlier. So the weight sharing loss is it's obtained by computing the mean squared error between the corresponding weights in the Marmousi network and the SEAM network. And for this specific example, the two network architectures are identical to each other in terms of the architecture. So it allows us to compute that loss. And then the total loss is a weighted sum of the regression loss, the reconstruction loss, and the weight mismatch loss, which is what allows the knowledge sharing to happen. And the gamma in this loss term is something that can be controlled. By increasing gamma, we can increase the network, we can pressure the networks to be in closer proximity to each other at the expense of optimizing on their respective data sets. If we increase gamma enough, it becomes the situation where you are training a single network on both data sets. Conversely, if we decrease gamma to a very low value, you end up with a situation where the two networks are virtually training independently of each other. But by setting gamma to a very appropriate value, what we do is we allow the networks to train and optimize on their respective data sets, but we also encourage them to find a solution within the proximity of each other to benefit from any mutually beneficial knowledge that they might have. So we show the results for this scheme after training using this scheme. We have the ground truth impedance for the SEAM as shown on the left, and the predicted acoustic impedance section on the right. And it can be seen that we obtain very high quality estimations in certain regions of the profile. So it's able to predict certain detailed structures within the location showed by the box. It's able to delineate the high impedance arch on the left. It's able to mark out with some accuracy the top of the salt dome, and it's also able to identify the transition between the low impedance region and the high impedance region at the right of the model, despite the seismic data being very noisy in that region. Similar to before, we perform an analysis of wells taken from the model at specific places, and then overlaying on top of the ground truth property trace, the traces predicted by the proposed scheme. And what we see is that the proposed methodology is able to perform the estimation. It's able to capture the low and the high frequency trends in the ground truth trace very closely. And doing a more thorough numerical analysis, regression analysis on the data set, we see that for the SEAM data set, we are able to obtain a higher performance with weight sharing as compared to without weight sharing. So everything else being the same, using the same networks and the same training samples and same number of training samples, we obtain a higher learning performance on SEAM with weight sharing on Marmousi with Marmousi as compared to learning on SEAM alone, as seen in the first table. And similarly with Marmousi, we see the performance without weight sharing is slightly higher, but that just goes back to the fact that we had a lot of training samples in Marmousi to begin with, and that by performing weight sharing on SEAM, we did not degrade significantly the performance on Marmousi, as would have happened with the conventional pre-training and fine-tuning based strategy. So the takeaway from this talk is that conventional inversion methods for reservoir characterization work in a trace-by-trace fashion, and that leads to poor lateral continuity. We also learned that learning-based inversion suffers overfitting due to the scarcity of well data. So, and the pre-training transfer learning scheme may not always work if the two data sets happen to be sampled from very different distributions. So we proposed to overcome the problem with 1D trace-by-trace models. We proposed spatiotemporal models that are not only able to model the seismic data temporally, but also able to inject the spatial neighborhood information into the seismic traces for improved resolution. On top of that, we proposed a joint learning transfer learning scheme that allows different networks different networks training on different data sets to benefit from each other while they're optimizing on their respective data sets. Both of these strategies should be kept in mind. They can be expanded to, for example, 3D spatiotemporal models, because seismic data sets happen in 3D structures. So one can very easily extend the spatiotemporal scheme to 3D convolutional networks, able to temporally model the seismic data, while also able to inject the 3D spatial neighborhood information into the network. Similarly, the joint learning scheme can be expanded to learning from more than 2 data sets. We do not have to be limited to 2 data sets, as shown with the example in this work. And we saw that the proposed approach leads to high quality estimations and greater generalization performance on a difficult data set with a low number of training samples than would have been possible learning on it alone. Lastly, I'm very grateful to my advisor for the guidance that he offered me throughout the time I was doing this work, to my teammates for their very helpful feedback and comments. To look at some of the other work that we've been doing, I highly recommend you browse our website. Our codes can be found on GitHub. The work that I just described can be read in much more detail with a lot more experiments in the journal that was recently accepted to Geophysics. The preprint for the journal and the codes for the journal, they are available. You can go to them by scanning these QR codes below. This work has also produced 2 conference papers containing some additional details that you might be interested in. So at this point, I'm open to any questions that you might have.
I believe there's a question in the chat, Ahmed.
All right. So for the losses, that's actually a very good question. And actually, let me go back to the slide that I have. So for the loss terms, there's 2 loss factors for the regression and the reconstruction losses. And for those, we just set them to 1. The tricky component here was the weight mismatch component, which is gamma. And we found over the course of our experiments that by setting gamma to a very high value, you end up in a situation where the 2 networks virtually learn at the exact same rates. And this might, in some trials, it might help the performance. In other trials, it might actually worsen the performance. So it's very initialization dependent. Setting gamma to a very low value results in the situation where the 2 networks are virtually training independent of each other, and it's almost like the situation where you have no transfer learning. But by setting gamma to an appropriate intermediate value, we found that you have the situation where the weight mismatch loss in particular, it decreases from a high value, but not all the way to 0. So when you have that kind of a scenario happening, that's how we knew that we had picked the right loss factor for that loss, because the networks are learning from each other, because as seen by the fact that the weight mismatch loss goes down, but they're not being forced to find the exact same solution. I hope that answers the question.
If you don't mind, I'm gonna unmute myself. Thanks for your talk. I'm really interested in your methodologies and stuff. I have a little question on the first part of your talk, where you map the RTM images to the acoustic impedance of your seismic model. Say, right now you have like what kind of seismic acquisitions did you use to take the RTM images? And would you think that matters for your machine learning model to recognize, to characterize the seismic traces?
Right. So for this specific experiment, we used migrated seismic images specifically for impedance model building, because that's what you commonly encounter in the literature. So, and then for the data set that we used, the migrated seismic section comes along with the data set. So we did not actually have to perform migration ourselves. Both the ground truth impedance model and the seismic section, they came along with the data set.
I see. Got it.
If I may ask a question. So, I think there's a previous slide from here. You said that you sort of choose the Marmousi model to be the generalization data set by taking out more well logs from that. And that's how you sort of declare that L will be the generalization, and then the SEAM will be the fine tuning. I'm curious what the proportions were, like how much more data did you grab from Marmousi to sort of establish that? Thank you.
Yeah, so I think I mentioned the number on the slides, even though it was a very kind of side note. So we sampled 14 wells for SEAM and 51 wells for Marmousi. And it's like exactly you said, the idea is to replicate the scenario that one would encounter in a transfer learning paradigm, that you have more training examples in a source data set compared to a target data set. Although for an image-based task, that proportion, the difference in the proportion is going to be much larger as here. So we wanted to respect that. So the number of training samples in Marmousi is not actually that much larger than what we have in SEAM.
Okay, thank you. Kind of a follow-up. So it seems like out of these losses, the one that has the weights of the networks, that is the main one that will allow the networks to talk to each other. Now, I may be wrong, but my intuition says that because the other losses have terms from both networks, like that regularization loss has an output from both your Marmousi network and your SEAM network, but there's also going to be some communication in between them.
Yeah.
Am I wrong there?
Yeah, that's a very good question, and my answer to that would be no. Not only because we verified that, but also because it can be seen that for the loss, take the reconstruction loss term coming from Marmousi. So that loss term did not have any contribution from the learning parameters for the SEAM network. And since, because of that independence, if you differentiate that loss term with respect to the other network's parameters, you're going to get a zero. It's just differentiation. Did I make sense, or? So it's kind of like, yeah, so it's kind of like, if I were to put that in very simple terms, it's kind of like you differentiate z with respect to x, and then there's no dependence of z on x. So you're going to get a zero in that case.
Yes, that makes sense. Thank you.
there any other questions? Well, if not, Ahmed, I just wanted to say thank you so much for sharing your very insightful presentation. I really enjoyed how detailed you were at explaining the different strategies you went to mitigate the overfitting problem, and your results really do show that they are working. The high quality and the better generalization overall from all your different approaches, from the joint learning to the different architecture design strategies that you implemented, all of them definitely paid off in the good quality and better generalization that you received from your proposed approach. And I just want to say on behalf of everyone, thank you. Thank you for presenting your research for us today. We really learned a lot, and we would love to have you back again soon.
Thank you very much, Yashi. I'm glad to be invited.
Yeah.